On November 20th, 1969, Apollo 12 deliberately threw part of its lunar module back at the moon. The empty ascent stage hit about 76 kilometers from a seismometer the astronauts had just installed. The instrument did not record one sharp jolt and then silence. The signal built for roughly 7 minutes, then kept reverberating for around 50 minutes. The startled description that survived was irresistible. The moon rang like a bell. But what did it actually mean? The answer is stranger and more useful than the hollow moon myth it later inspired. This is Pip's Fact Orbit. One familiar fact and a much stranger story. To understand that famous ringing, start 4 months earlier with Apollo 11. Neil Armstrong and Buzz Aldrin placed the first seismometer on another world. It could feel vibrations moving through lunar rock, just as instruments on Earth record earthquakes. It worked for only about 3 weeks, but it proved the technique. Apollo 12 returned with a longer-lived station as part of the Apollo Lunar Surface Experiments package, or ALSEP. The station needed known impacts for calibration. Natural moonquakes do not arrive with a label telling scientists their exact location, time, mass, and speed. A discarded spacecraft did. After Pete Conrad and Alan Bean rejoined Richard Gordon in lunar orbit, controllers commanded the ascent stage of the lunar module Intrepid to crash. It struck at about 1.7 kilometers per second, with an impact energy NASA compared to roughly 1 ton of TNT. Because the time and trajectory were known, scientists could watch how that energy traveled. The first motions reached Apollo 12's instrument quickly, but the trace did something unfamiliar. Instead of peaking immediately and fading cleanly, the vibration gradually grew, reached its maximum roughly 7 or 8 minutes after impact, and then decayed with extraordinary slowness. The Apollo 12 mission report measured about 50 minutes of signal. Contemporary NASA accounts described stronger motion for more than half an hour and weaker reverberation lasting close to an hour. The result was especially surprising because the experiment nearly did not happen as planned. The ascent stage had to be steered into a useful impact corridor after it separated from the command module. Its exact crash point was reconstructed from tracking and seismic timing. This was not destruction for spectacle. The vehicle had finished its job, and its final motion supplied a rare piece of controlled data. On Earth, geologists can set off small explosions or use mechanical vibrators to send known pulses underground. Apollo adapted the same basic logic on a planetary scale, using hardware that was already destined to be discarded. Every measured second after impact became information about the ground between the crater and the station. That is where the Bell comparison came from. It was a description of the seismogram, not a microphone recording. There is almost no atmosphere on the moon to carry audible sound outside, and nobody heard a giant metallic tone. Seismic waves were bouncing and scattering through solid lunar material. Calling it ringing captured the long, slowly fading trace. It did not mean the moon was hollow. So why did the trace last? Earth is geologically noisy, but its rocks also contain water, pores, fluids, and layers that absorb and redirect energy. On the moon, the shallow crust is extremely dry and has been fractured by billions of years of impacts. That combination gives seismic energy fewer efficient ways to die out. Waves ricochet through a broken, low attenuation landscape. Their paths become scrambled, so energy arrives over a long interval instead of as one neat pulse. Think of dropping a stone onto a solid slab, then into a vast pile of dry, cracked blocks. In the block pile, energy can take countless routes before it finally disappears. The lunar signal's long tail tells scientists about scattering and damping inside the moon. It is evidence about the moon's structure, not evidence of an empty interior. Measurements from Apollo also revealed a layered body with a crust, mantle, and small core. Apollo 13 made the experiment even more dramatic. Long before the oxygen tank explosion that changed its mission, the Saturn rocket's third stage was aimed at the moon. On April 14, 1970, that SIVB stage, weighing about 13,400 kilograms, struck at roughly 2.6 kilometers per second. Apollo 12's seismometer detected the impact from about 135 kilometers away. The resulting signal continued for 3 hours and 20 minutes. 3 hours and 20 minutes sounds unbelievable if imagined as a literal bell tone. On a seismic record, however, It means an extended tail of weak motion after a huge known impact. Later Apollo missions repeated these control crashes. Each one gave scientists another pulse with known energy and location, helping them probe the lunar interior much as doctors use waves to look inside a body. By 1972, Apollo astronauts had installed a 4-station seismic network. It operated until 1977 and recorded thousands of events. Some are artificial impacts. Others reveal that the supposedly dead moon is not perfectly still. Scientists now group lunar seismic events into 4 broad causes. Deep moonquakes occur hundreds of kilometers down and repeat in patterns linked to tidal stress from Earth's gravity. Meteoroids strike the surface and create impacts of many sizes. Thermal moonquakes happen as the surface expands and contracts during the enormous temperature swing between lunar day and night. And shallow moonquakes occur near the surface. These can be the strongest and are probably connected to faults and the moon's gradual cooling. That cooling matters because the moon is slowly shrinking. NASA's Lunar Reconnaissance Orbiter has photographed thousands of small thrust faults, where one section of crust is pushed over another as the interior contracts. Researchers have connected some Apollo-era shallow moonquakes with these young fault scarps. The moon's diameter is estimated to have decreased by more than 50 meters over the last several hundred million years. That is tiny compared with the moon itself, but enough to wrinkle and crack its crust. Apollo's instruments recorded 28 shallow moonquakes, some estimated around magnitude 5. Unlike an earthquake on Earth, lunar shaking can persist for many minutes because the same dry, fractured rock that prolonged the spacecraft impacts also lets natural vibrations reverberate. A moderate event close to a future base could stress equipment, disturb steep slopes, or damage structures designed without lunar shaking in mind. There is one important limit to the Apollo data. All 4 long-lived stations sat on the moon's near side, within a relatively small region. They gave us a revolutionary first map of lunar activity, but not a complete global picture. Modern missions can place more sensitive instruments farther apart, including near the poles and eventually on the far side. That would help locate quakes more precisely and reveal how different regions transmit energy. For Artemis crews and long-term lunar outposts, this is not trivia. Engineers need to know how often strong shallow events happen, how slopes respond, and which ground is safest for habitats, power systems, landing pads, and buried cables. A strange trace from a deliberately crashed spacecraft became the beginning of lunar hazard science. So, did the moon ring like a bell? As a metaphor for an amazingly persistent seismic signal? Yes. As proof of a hollow moon? Absolutely not. Apollo 12's impact reverberated for about 50 minutes. Apollo 13's rocket stage produced a signal lasting 3 hours and 20 minutes. And the reason lies in the moon's dry, battered, weakly damped rock. The phrase survived because it sounds mysterious. The real discovery is better. The moon is a layered world that still shifts, cracks, and records its history in waves.